Good morning or good afternoon. My name is Cole Porter, and my video presentation is going to be on the four fundamental forces of nature. The four fundamental forces are, in no particular order, gravity, electromagnetism, the strong nuclear force or strong interaction, and the weak nuclear force or weak interaction. These forces are the driving reason behind every physical interaction that goes on around us every single day. And these forces help us understand how planets rotate and how objects fall, the behavior of magnets, electricity, the structure of nuclei, and radiation. And we'll be going into detail on what these forces are and how we use them every day in our lives. So the first force we'll be discussing is the force of gravity. Force of gravity describes the interaction between two objects of certain mass and a certain distance away from each other. And so gravity is a function of mass and distance. So the greater the mass between, or the greater the mass of either object, the greater the force of gravity. And the greater the distance between them, the weaker the force of gravity. So we can tie these two variables together by using the gravitational constant. And we find that the force of gravity equals the gravitational constant times the mass of objects 1 and 2 divided by the distance between those objects. And this equation also helps us describe the force of gravity that any object applies to things around it. And that equation equals the force of gravity equals the gravitational constant times the mass of the object divided by its radius. And so we can find the force of gravity that the Earth applies to objects. We know the mass of the Earth, we know its radius. So when we plug those numbers in with the gravitational constant, we find that the gravity on Earth equals 9.8 meters per second squared. So with 9.8 meters per second squared, we can use this in kinematic equations. So we know that the potential energy of an object equals its mass times gravity times height. The force of a falling object, we know the velocity of a falling object, we know the distance traveled of an object in a certain time. And with these equations and others, we can build airplanes and rockets. We can understand planetary and solar orbits. And any other problem that we run into that involves gravity, we're able to solve because we know what the force of gravity is on the Earth. And that's just a quick overview of what gravity is and how we apply it. The next force that we'll be looking at is electromagnetism. And electromagnetism describes the interactions of both electricity and magnetism. And so we know from electricity that two like charges repel and two opposite charges attract. And we learned from magnetism that magnets can create these magnetic field lines and have interactions with other magnets and metals and moving charges. And so although these seem to be different things, they are in fact one unified force. They're interactions between electrons and protons. They're all basically moving charges. And these forces help us understand chemical bonds, interactions, reactions, physiology. Everything that happens in the human body is a function of electromagnetism, hormone binding, electrical impulse signals, membrane potentials. Everything that occurs in our body is a function and it is derived from electromagnetism. So understanding electromagnetism is very useful, and of course it helps us understand magnets, which are super fun. So the next force we'll be taking a look at is the strong nuclear force or strong interaction. Now, this force describes the interaction that occurs within a nucleus. Basically, two protons, because they're both positively charged, would normally repel each other. But the strong nuclear force is what holds the nucleus together. It is the interaction between protons and neutrons within a nucleus. And it's a very strong force. It's actually 10 to the 38th time times greater than gravity. The problem is that it's only effective over small distances. And so outside the nucleus, that force isn't really interacting anymore. And so we see that even within a bigger nucleus, the force, the strong force, becomes weaker, which leads to the instability of extremely large nuclei. And now we have exploited this principle in creating atomic bombs. When you separate a neutron or neutrons from the nucleus and protons, there's a lot of force between them, and that release of energy is what causes a chain reaction and for the atomic bomb to explode. And now we also use this principle in nuclear energy. And so this force is super important because it is a huge source of energy in our country, and it is super interesting. So the last force that we'll look at is the weak nuclear force, or weak interaction. Now this force describes basically a form of radiation known as beta decay. And with this force, a neutron decays and becomes a proton and emits an electron or positron. And so if we look at a beta decay reaction, if we start off with one atom basically of thorium, which has a atomic number of 90 protons, one of its neutrons will decay and it will emit an electron and become protactinium with 91 protons. And so it becomes an entirely new element through this weak nuclear force. And similar to strong nuclear force, it's only effective on subatomic particles. It's not effective at a great distance between neutrons and nuclei. And so it helps us understand some forms of radioactivity, beta decay, beta emissions. It helps us understand decay of mesons, and it's what basically powers nuclear fusion of the sun. And researchers are looking into this force to understand it better so that we can start producing energy through nuclear fusion. And that it's a cleaner way of energy, and it's something that's researchers are looking at doing in the near future. So those are the 4 fundamental forces of nature. I hope you enjoyed this video presentation. Anyways, yep.